Welcome everyone. Formally, I am very happy to tell that today we have Professor Ulrich Nowak as the speaker. So a very old friend of mine, and we had some overlap in Duisburg, where I did my PhD, and Ulrich also had his almost entire education in Duisburg. And really, I'm very happy and privileged to introduce Professor Ulrich Nowak. And I also really like to thank all the audience who are here to join this webinar. Today is, I think, the 94th webinar of this webinar series on spintronics. And it's all because of you and the speakers like Ulrich. We are able to continue this, and hopefully we'll continue at least to achieve the 100 and maybe more. And so very nice interactions are happening. So yeah, so again, good morning, good afternoon, good evening, wherever you are. And I think Ulrich is very well known in this community, but nevertheless, there are a couple of young students. For their benefit, I would tell a few words about Ulrich's academic profile. So he got his diploma in 1989, then PhD in 1992, and habilitation in theoretical physics at the Gerharder Mercator University at Duisburg. Actually, it was funny because I got admitted in 2002 in Gerharder Mercator University, but I think later on it was changed. So I got my PhD from University of Duisburg SM. And after the habilitation, so Ulrich was in Pittsburgh, in Duisburg also as a scientific assistant. Then he moved to University of York in UK. Between 2005 to 2008 as a lecturer, then reader in the Department of Physics. Then he moved to back to Germany as a full professor of theoretical physics at University of Constance, where he is currently working. And he was the head of the Department of Physics from 2018 to 2020. And he has got several awards and honors to his credit. One of them is the Lux Award for the best teaching at University of Constance. Then he became the senior member at the IEEE Magnetic Society, and he was also the elected member of the Senate of University of Constance, and so on. And he has like more than almost 200 publications with nearly 8,000 citations. His research interests are quite broad and very current topics. So of course he's a condensed matter theoretician. Have a lot of interest on computer simulation and multi-scale modeling. He's definitely focusing on magnetic material properties, and in particular various aspects of spintronics. Also, he looks at alternate phase phenomena and optomagnetic effects, topological spin textures, and that's the topic of today. So again, many thanks, Ulrich, for kindly agreeing and sparing time from your holiday to give this talk on behalf of my entire team. Braj, Puspendra, Sakti, Ajar, Kiti, Soyan, and all. I'd like to thank you on behalf of everyone. I'm grateful that you could join, and we are really looking forward to the lecture. Before we start, I just like to mention that during the lecture, we don't take questions. So if you have any question, kindly write in the chat box or raise your hand. At the end of the lecture, first we will take a group photo, and then we will have the question answer session. Yeah, so with this, I request Ulrich, the stage is yours. Please start your talk. Looking forward. Thank you.
Yeah, thank you very much, Shubhankar, for this very friendly and detailed introduction. And thanks for the invitation and the opportunity to speak here. So, as Shubhankar said already, my group works in the field of spintronics from the theoretical side. Theory, but mostly numerical methods and computer simulation. So we work on ultra-fast spin dynamics, spin transport, different aspects. But today I'm going to talk specifically about skyrmions, or a bit broader, topological spin textures. And we are especially interested in thermodynamics or thermal effects. So the people in my group who work in these projects are here. Most of the things I show are from Markus Weissenhofer, a PhD student in our group, or from Levente Rocha, who's currently postdoc. But there's also Daniel working in his master's, and Andreas Donges worked earlier. He has left in this topic, but he has left my group. But this work also benefits from collaborations, on the one hand with a group of Laszlo Szymlok in Budapest, who works on initial calculations. And then from the experimental side, we collaborate with Matthias Claudy's group from Mainz University, and I will show a couple of experiments from him. So skyrmions are localized magnetic textures, and I will show that you can use them in certain devices. One of them where you need the Brownian motion of the skyrmions is a reshuffler. Now that's what is shown here on the picture. I will come to that a bit later. So I will start with an introduction on skyrmions and topology, and you will see that skyrmions are like particles, and they show Brownian motion, statistical motion due to thermal fluctuations. And I will then explain how we model that in a multi-scale modeling picture, where you start from first principles and go via spin models to a quasi-particle descriptions of the skyrmions. But let's broadly start with the motivation. So much of the motivation to work in spintronics comes from the idea to improve electronic devices, let's say, by some spin degree of freedom. And 10 or 20 years ago, one would have said that it is important to get everything smaller, to go towards nanostructures, to improve density maybe of the storage, or to get everything faster. But nowadays, I would say some of the motivation to work in the field is to reduce energy, because the reduction of energy consumption might help saving our climate problem. And even the IT sector, and that is shown here on the slide, is important. According to this study here from the Royal Institute of Technology in Sweden, currently 10% of the electrical energy goes into the internet. I mean, that is a vague number because it's not that well defined what exactly is the internet, but that is a bit broken down here on the right-hand side. It is data center devices, network, and so on. So everything together takes a certain part of our energy consumption, and this is always increasing currently. So even here it is interesting to save energy. There are certain ideas around how one could do that by changing the energy in electronic devices, the energy conversion or the energy consumption. And one idea is to take the spin degrees of freedom as well, or use combined transport properties like heat and spin transport. That was a big effort 10 years ago or so that started in this area here, spin caloritronics, spin Seebeck effect. You can create spin voltage or spin currents in a temperature gradient. You can convert energy here. I will not go here into details, but what came out here as a side product is that we realized that there are two types of spin currents. The more usual way to think about that is that you have electrons that move and they are spin polarized. That gives a spin current. But there's also the possibility in an insulator that you do not move the electrons, but you have a waveform excitation of the magnetic ground state, magnons. And these magnons, they also carry spin. So there's also a spin current because of a magnon transport. And that can be in an insulator without a charge transport, and that costs less energy. So it's interesting to think about spin transport in insulators, and the largest class of insulators by far is the antiferromagnets. There are much more antiferromagnets than ferromagnets. Those were for a long time thought to be rather useless because they don't have a magnetization. But in recent years, it has been realized that even in an antiferromagnet, one can read the order via anisotropic magnetoresistance. At least the switching of 90 degrees you can read with resistance measurements, and one can write because even certain types of antiferromagnets react to currents. That gives new opportunities to think about storing information, for example, in antiferromagnets instead of ferromagnets. They have certain advantages, but also here I will not go into details, but I will present you an idea that goes a bit more in the direction that I will talk about in the following, namely new ideas for storage. So currently information is stored in magnetic devices in form of a domain structure that is static. And in a hard disk, then the disk rotates. There are ideas around in the future to store the information in domain walls that you can push around. Goes back to work of Stuart Parkin. And instead of domain walls, one could also use skyrmions, as shown here. So a skyrmion is a magnetic texture, and in a thin film or in a track, it is a localized structure. You could say it is like a bit. And interestingly, it is rather stable, and you can push it around. So it reacts to currents, and with that you can push it. So you can move it, you can control it, and they are stable, so they're interesting in a way. And you can use them, for example, that's one of the ideas in probabilistic computing. I will come to that a little later, but first I will explain, so what is a skyrmion? So as I said, it is a magnetic texture, and it looks like that, like shown here. Maybe if I start historically, it was first originally a model for a nuclear and has nothing to do with the magnetic system. But then there was a prediction that these structures should exist in magnetic materials. Then they were discovered, so they exist in bulk materials, and then later, that is this work here, in thin films. And now it's interesting because in a thin film, they can be used for something, let's say. And they look like this. Maybe we look here to the right. A skyrmion is in a magnetic film that is otherwise ordered, let's say in the blue direction. It is in the center pointing in the opposite direction, let's say down, and then around it is kind of a vortex structure. Could also be like this. And why is that interesting? It is interesting because it has something to do with topology. So topology is rather new aspect in physics. It comes from mathematics, but it has then been realized that it plays a big role in physics, and it led to recently to the Nobel Prize for the first topological work in condensed matter physics, let's say. Topology is about the deformation of objects without destroying them, so continuous deformations. In terms of a magnetic thin film, it means deformation of a vector field, you could say, the magnetic structure. How can you deform it continuously or not? So there are certain structures that you cannot reach by a continuous transformation. That's exactly the case for a skyrmion. So skyrmion is a structure that you cannot unwind back to its original ground state. So if you look at this structure, you could say, okay, the ground state is blue. Okay, everything pointing upwards. So can I grab this spin, the yellow one, and rotate it back in the blue direction without destroying the order? And you cannot, that's the point, because you would have to make a decision in what direction will I rotate it, let's say in the red one. Then you wind up this here, this wall. But on the other hand, you will have a second wall on the other side, okay, because it can only wind up in one of the directions here. So you cannot get rid of this structure. So, and that is called topological protection. And one can quantify this by this integral. So you can calculate this integral over this, let's say, two-dimensional structure. And in case of a skyrmion, you will get a 1. And in case of the ordered state, you will get a 0. And that can be understood a bit by a projection of this structure on a unit sphere. So if you see in this structure, all colors appear somewhere. So one could say that this structure could be mapped on all spin directions of a unit sphere. So every direction appears somewhere, the red one, the yellow one, and so on. And that is typical for a skyrmion, and that is what is quantified here with this so-called topological charge. So if it is 1, then in your spin structure, you can be wound around the unit sphere once. Here's some example for spin structures. So the ground state, all blue, if you calculate this integral, has topological charge 0. And all structures that you can reach by a continuous transformation, like this one here, where you rotate the central spin to the right, then you will get something like this. That has also a topological charge 0. But the skyrmion has topological charge 1. If you would do this projection from the last slide, this one here, all blue would just be, oops, sorry, I have to go, all blue would just be 1 point on the unit sphere, right? And this would be half the unit sphere covered, but not all direction. That gives in this integral also a 0. Only the skyrmion gives a 1. But there are many ways to do that. You can rotate all the spins in this vortex by 90 degrees, then you get something like that. Same topological charge, or this or that. There's also a -1. If you rotate this vortex in the other direction, then you get a topological charge -1. And you can also build structures like that. Here, all directions appear twice. For example, red is here and here, or light blue is here and there. So that is topological charge 2. One could give all the structures names. The real skyrmion is that one, Q equal 1. That is called anti-skyrmion, Q equal to -1. The higher orders don't have really names. So in the following, I will just call all of them skyrmions, because we will play with this topological charge. All of them I will call skyrmions or skyrmionic structures, and I will tell you which charge they have. Okay, so what can we do with that? There are very interesting effects. This here, the movie shows the simulation. So in a, let's say here, sorry for the different color coding, in a yellow oriented two-dimensional film, this would be a skyrmion in a computer simulation. And at final temperature, it behaves like a particle in a heat bath, because we are at final temperatures. And because of the heat bath, it starts a Brownian motion, like a nanoparticle in a fluid. So there is diffusive motion of skyrmions. That can even be used experimentally. So on the right-hand side, now I show you a movie. I have to explain to you what it shows. It's not that easy to see. So this movie is from the collaboration with a group of Matthias Clauy in Mainz. So they measured this here. And this is the diffusive motion of skyrmions in real life. What you see here is like a track coming from the left. Then there's a chamber. Then there is another track going to the right. Okay. And the skyrmions, because of an electrical current that is applied here, they move from left to right. But the interesting point is that at the same time, they show a diffusive motion. So I start this again. So have a look at in the chamber, for example, here, this is a skyrmion. You see they don't just move from left to right, but at the same time, they show a diffusive motion. That was the first measurement of diffusive motion. And the point is here, this is like a device. And that is a device where you could say you have an input, that's where the blue line is, entering the chamber, and an output, leaving the chamber. Interesting fact is, because of the diffusive motion in the chamber, the input and the output signal are not correlated. That's what is shown here. It's a bit more tricky, the experiment, but I will skip the details here. These are really two chambers, and it's about the correlation of the two chambers. But that is not important. So the rough idea is you have an input signal and an output signal, and the two signals are uncorrelated because of the diffusive motion. That means you can use that as a reshuffler device. Okay, reshuffler. Now we could ask a question, what is that and why do you need it? A reshuffler device is needed for probabilistic computing. So what is what is probabilistic computing? The next question. Sorry, I've currently a small problem with the computer. I hope that recovers. Okay, do you see the slides again?
Not yet.
Then I have to share again.
Yeah, we see it.
Okay, good. So what is probabilistic computing? That is a different way of computing, not like the usual way. It is about computation with, you could say, with the random bit streams. So you use noise. So you have a stream of bits, let's say zeros and ones, something like that. And you can do computation with that. For example, if you take a logical AND of 2 bit streams, okay, then the probability for the result would be the product. Okay, so if that has probability PA and this PB, the result after an AND operation would have probability PA times PB. That is statistically correct, but it's not only in the limit of large signals and only if they are uncorrelated. Because imagine for a moment that you would have two correlated bit streams, so they are identical, like in this example here. Then after an AND, you have the same stream, but this is not the case, that PA times PA is equal to PA. So in other words, to calculate with random bit streams, they have to be uncorrelated. And that's exactly what a reshuffler device would do. And that was the idea that we published in this work here, namely that one could use the Brownian motion of skyrmions for a reshuffler device by creating two, and that is one of the devices you would need to decorrelate two bit streams. Okay, so we have understood a couple of things, skyrmions, what they are, and that one could possibly use them for probabilistic computation. So now a bit more in this, on the theoretical side. So what does that mean, this Brownian motion of skyrmions? The question is, how do we describe that? So in the following, we'll start with this here. How we will describe this? We will use spin models in the following, that follow an equation of motion. And this slide gives you a bit of an overview what methods exist for the numerical treatment, let's say, of magnetic properties. And that's a very, very personal view, you could say. So on the x-axis, I have the, let's say, how microscopic the theory is. So it could be electronic structure, or a bit more mesoscopic spins and atoms, or a continuum theory, micromagnetism, or even quasi-particles. And here it is on the y-axis what you can do with that. So you could calculate static properties, dynamic properties, or even thermodynamic properties. And there's not one method where you can do everything at the same time. So we could do first principle calculations, then we get some material properties. But with that, you calculate only ground states, let's say, normally. So you get static properties, but from first principles. If you are interested in dynamics or thermodynamics, you can do what I will show you in a second. You can do spin model calculations with the Landau-Lifshitz equation. But then you lose a bit of these details, or you do more macroscopic description. And what I will explain to you for the rest of the talk is how one can link that, because that's what we are working on, multi-scale modeling. So we do the spin model simulations, but we want spin model parameters from first principles. And we will also compare with more mesoscopic calculations based on a quasi-particle picture, but the skyrmions are like particles. Okay, let's start with the spin model. Spin model is something like this. So you have spin degrees of freedom, okay, and we've seen that certainly before in a seminar on spintronics. In the easiest case, that could be a Heisenberg model, okay, so spins want to be aligned if this is a ferromagnetic interaction. And then you can have more interactions or energies, let's say a Zeeman contribution, a coupling of the spins to a field, some anisotropy, let's say a uniaxial anisotropy in some direction. And for skyrmions, you need also a Jaruzelski-Moria interactions normally. There are different ways how you can produce skyrmions, but that is, let's say, the most effective way. Jaruzelski-Moria interaction is a cross product. It appears only under certain conditions, and it has something to do with the inversion symmetry of the crystal that you have. for a thin film, normally the inversion symmetry is broken at the interface. And if you have a lot of spin-orbit coupling, for example, interface to a heavy metal like platinum or so, then you will get some Jaluzinski-Moria interaction at the interface. And this cross-product means that the spin structure will somehow be twisted. Okay, so it will not be just ferromagnetic somehow, but somehow twisted. The ground state could now be, depending on the details of this interaction, a spin spiral or so. And in connection with anisotropy in field, it can be a skyrmion. So this twisted structure comes from the Jaluzinski-Moria interaction in that case. Sorry, I have sometimes problems currently with the computer. Okay, here we go again. So, for a specific material, we calculated now all the interactions in the Hamiltonian. That is a lot of numbers that you have. It's not easy to get that, let's say, from experimental facts or so. But you can do that with certain types of first principles calculation. For example, with this here, in SKKR method, fully relativistic, because you need the spin-orbit coupling. And that is work done by Levente-Rocha in the group of Laszlo Szűnyök, with whom we are collaborating. And for a specific material, and this is our working horse, you could say, that is an iron layer covered by platinum iridium on a palladium surface. Okay. And here you get a lot of Jaluzinski-Moria interaction because of the symmetry breaking and the large spin-orbit coupling. And you can calculate all these interactions from the Hamiltonian that I showed you on the slide before. And it looks a bit like that. So the sign convention is the isotropic exchange is here ferromagnetic, but then there's frustration because the second and the third neighbor interaction is antiferromagnetic. So it is a bit frustrated exchange, but also Jaluzinski-Moria interaction. And that one can be scaled with X, that is the amount of iridium in the platinum iridium layer. Now we can play games. So we can kind of tune the Jaluzinski-Moria interaction, but at the same time we are frustrated at an exchange. And that leads to the fact that you can stabilize skyrmions and other skyrmionic structures with a topological charge ranging from -2 to 3. I will show you that later on a slide. And they can all be stabilized a bit depending on an applied external magnetic field. And then in computer simulations, you can investigate their behavior. You can also calculate the skyrmion interaction, which can be attractive. That is rather unusual, but in that model system here, it can be attractive, as shown in this paper. And then you get clusters, even clusters of skyrmions like that. But I will not talk about clusters in the following, but individual skyrmions and their behavior. How do we do that? Maybe one word on the simulations. So once we have that model, what we do is we solve the equation of motion for each of the spins, SI. And that is the Landau-Lifshitz equation that you have probably seen before somewhere. We do that in the stochastic version. So our effective field here, which is the gradient of the Hamiltonian with respect to the spin, that contains also a random component, a noise component, theta of t. And you can calculate the properties of the noise. So here we use that the average is 0, and the correlations look like that. So it's a white noise, and you could say the strength of the noise is given by the damping constant alpha that appears here in this term, in the dissipative term, and also by the temperature. If you do that all properly, what happens is that you simulate a multi-spin system in the canonical ensemble. That means in a heat bath. So there is a heat bath that defines a temperature T, and your spin model is in that heat bath. And all properties that you can calculate, the time average of them converges to statistical averages in the canonical ensemble. So in other words, you can calculate dynamic properties, Magnons, thermodynamic properties, thermal properties, phase transitions, and things like that. There is an example here, a phase transition. So that's a magnetization of some ferrimagnetic material, dysprosium cobalt, has two sublattices, and you can, in a simulation, calculate the thermal properties. In that case, it is a reorientation transition from out of plane to in plane, then a phase transition to paramagnetic. All that can be calculated in principle. You need a lot of computer power for that. We simulate sometimes up to 10 to the 8 spins. Okay, that is doable with certain methods on graphic cards and highly optimized. There's a slight disadvantage I should mention, namely that we treat the spins as classical vectors. I mean, quantum mechanically they are operators, right? But we can only calculate the classical limit where they are unit vectors, which means in the Magnon picture that we simulate the limit of high occupation numbers. So this method is good for higher temperatures, not so much for low temperatures. The quantum mechanically, the behavior of the Magnons is different. Okay, fine. So what can we do with that? Now we can now simulate the skyrmions as I showed in the movies before. So we have this monolayer of iron. We take a large system, 10 to the 5, 6, 7 spins. We have skyrmions in the model. We can define a center of mass, a position of the skyrmion, and then calculate, for example, the mean square displacement. And because of a finite temperature or temperature dependent, that's shown here, they move diffusively. So the mean squared displacement grows linearly in time. That's what you expect for diffusive motion. That would also be in Langevin dynamics or Brownian motion, mechanical motion. And you can define a diffusion coefficient d. Okay, that's fine, you can do that. You will find in our simulations that this d is proportional to the temperature. That's what you roughly see here with your naked eye, maybe. Okay. And then there is some theory for that, for this diffusive motion. That was done by Schütte et al. In 2014. That rests on an equation of motion for the skyrmion as a particle in a quasi-particle picture. And I will explain that a bit later. But anyway, so there is, let's say, a theoretical forecast that the diffusion coefficient should behave like this, kBt, and then this fraction here. And that depends on two quantities, or three. Let's say one is the Gilbert damping constant, but the other two quantities are d and the g. The g is the topological charge, more or less, with some prefactors. So that is a quantized quantity, you could say, something like 1, 2, 3, or so, depending on the topological charge. And that's what we play around with here in this graph. And the other one is another integral. That's not the topological charge, but it is the integral that characterizes the, let's say, how the spin structure is twisted. And that comes along with the damping constant. So you could say alpha d here is a measure of the dissipation, and g is a measure of the topological charge. And the interesting point here is that there's a big difference whether g is finite or not. Because if g is 0, then you get a 1 over alpha. And if g is finite, then you get an alpha dependence. And that's what you see here. So that means the diffusive behavior of the spin textures depends on the topological charge. And q equals 0 is an exception. So topological trivial is very different, 1 over alpha, from topological non-trivial textures, which have a finite q. So the authors in that study called that suppression of diffusion. Okay, so because q equals 0 has a very high diffusion coefficient. Okay, and if there is something topological, a finite topological charge, then you get orders of magnitude lower diffusion coefficients, because low alpha, that's what is realistic experimentally here somewhere. So they call that suppression of diffusion by the topological charge. So we can play around with this topological charge because, as I said, in our model system, this iron monolayer between platinum iridium and palladium, we can stabilize different topological structures, and that's what they are shown here again. So that is a normal skyrmion here, but there are also others like an anti-skyrmion or a structure with Q equal 2 here, and that is Q equal 0. That is topologically trivial because you could unwind this structure and could transform it continuously back to the ground state. But it's nevertheless, it's not protected by topology, but it is stable in our model system here. That's what's finally shown here. So we played around with all this. We created on the computer all these different skyrmionic structures. We observed them while they were the diffusive motion. And then we see they follow mostly the theory. There are some exceptions and they are interesting. The one is some of these structures are not rotationally invariant. So they have a shape, you could say, like this one or that one. You see here's like an axis. It is a bit longer in this direction than the other. That depends on the details of the interaction, right? And if they have shape, that means that also their diffusive motion is anisotropic. So it's different in the one direction as compared to the other. And that's what we tested here. So Q equals 0 and Q equal -1, they are both not rotationally invariant. And then the diffusion coefficients in X and Y direction, they are really slightly different. So that's a bit more complicated than here, where that was averaged out. That was published here in this work by my PhD students. There's also some theory. You can do this also with the Thiele equation. There's maybe, I show again, there's also another difference. I will come to that a bit later here. You see for small alpha, you see also there's some deviations of our simulations from the theory. I will come to that. Okay, so how can we understand that a bit more in a multi-scale modeling picture? You can treat the whole skyrmion in this magnetic heat bath also as a particle that follows an equation of motion. So don't have all the equations of motion for each spin, but just one, assuming that the texture, the magnetic texture of the skyrmion is rigid. And that is called Thiele equation. The Thiele equation exists also for domain walls and vortices and whatnot. You can do that with all sorts of stable textures. You assume there is a certain ground state texture, let's say, and that does not move anymore. And then you kind of average out all degrees of freedom, and then you come up with an equation of motion for the center of mass, maybe also for other quantities. In the case of a domain, well, also the angle could get another equation of motion also. And in our case, for skyrmions, the Thiele equation looks like that. It's expressed in terms of velocity of the skyrmion. And it has, once again, these factors that I explained already. There's the one that is more or less a topological charge, and the alpha d, which is more or less a measure of the dissipation. And for the diffusive motion, you have to assume that this like acceleration, and that is given by the force, and in terms of long-run dynamics, that is a thermal force. So that is a stochastic equation of motion. The cross product here comes from the fact that in the Landau-Lifshitz equation, there are also cross products, and you average over that. And from that, you can calculate, first of all, the diffusion coefficients, and then you see that this number here is not just a number, but it is a tensor, and it has elements different. In the case of non-spherical skyrmions, these numbers are different in X and Y direction, for example. That's what I showed you on the slide before. But it's even more interesting. There's also this fact that I showed before, that there are some slight deviations from the analytical solution of the Thiele equation. And if we looked into this more carefully, by going to lower and lower values of the damping coefficient alpha. So in the first graphs, we went down to 10 to the -2, and that looked pretty good compared to the simple theory. But if you go towards 10 to the -3 or 4, you see there are big deviations. So the dotted line here, that is the theory of the Thiele equation, and the points are our simulations. And you see, the higher the temperature and the lower the damping, the bigger is the deviation. So where does that come from? That has a certain reason that is rather tricky. I try to explain. This was the graph I showed before. So when you go to the quasi-particle equation of motion, the Thiele equation, you assume that you kind of average your spin model and assume a rigid form shape of the skyrmion. In the original spin model, you had a heat bath. And with this damping constant alpha, you were coupled to the electronic or phononic degrees of freedom, let's say, of your material, okay? In the Thiele equation, that becomes this alpha D. But there is now another heat bath, and that's the point. There's another heat bath, namely, the skyrmion also interacts with the magnons. So the rest of the film would be long-range ordered, but not in the ground state. We are at finer temperatures. So we have interactions of this skyrmion also with the magnons. And they are not described as a heat bath in the Landau-Lifshitz equation because you really simulate or you describe the magnons in the spin model. And in the Thiele equation, that is kind of neglected. So the magnetic heat bath goes to a constant value of the background. So this part of the noise, you could say, is averaged out. And one can kind of repair that, but by assuming there's another heat bath, namely the magnons, and you couple the Thiele equation to another heat bath, which is given by the magnons. But here, the magnon number is now temperature dependent. So at 0 temperature, there wouldn't be any magnons, but at higher temperatures, there are some. So in other words, this coupling here is temperature dependent. And one can repair the Thiele equation by assuming another dissipative term that depends on the temperature. And this eta here would be the strength of the coupling to the magnons. And then you can recalculate everything and then it works. And these are, that is now a new solution of this extended Thiele equation with the magnon bath. And these are the dashed lines here in the graph. And now you see this agreement once again is perfect. So in other words, the Thiele equation is not sufficient to describe the coupling of magnetic texture to the magnonic heat bath, and that so if you have many magnons, higher temperature or high coupling to that, or a low coupling to the other heat bath, a low alpha, then it becomes important. This is not only a correction for the diffusion coefficient, by the way, it also changes the Skyrmion-Hall angle. So with this theory, so we would forecast the Skyrmion-Hall angle should depend on temperature, which it does not otherwise. I haven't explained what that is, but maybe for the experts. So that is another side result of this simulation. So we would say if you measure Skyrmion-Hall angles at different temperatures, you should get different results. And that is not the usual theory. That would just be this first part without this eta cube. The last slide I wanted to show regarding results is now what happens in a temperature gradient. So I showed already, okay, at final temperatures, skyrmions, they move, they have Brownian motion, they can be described as quasi particles. What is in a temperature gradient? What this graph here shows is the trajectories of skyrmions with different topological charges. We simulate them in a temperature gradient. So in our simulation, this gradient is very large because we have small skyrmions and small system sizes. Anyway, so to the right is hot, to the left is cooler. And now you see with different topological charges, you get completely different trajectories. All of them move. So that is the first thing we can say. So skyrmions in a temperature gradient move systematically. So in addition to the Brownian motion, we have also a motion, in some direction. One could call that the Skyrmion-Seebeck effect, motion of particles in a temperature gradient for electrons, or that called Seebeck effect. So we could call that Skyrmion-Seebeck effect. But there's also some angle, so they don't move just to the right or just to the left, but under some angle. And if there is a perpendicular component in the temperature gradient, that is called Nernst effect. It exists also electronically or for spin. It's also spin Nernst effect. So this could be called the skyrmion Nernst effect. And the trivial structure, Q equals 0, moves to the cold direction. This is this one here, Q equals 0 red. That's interesting. So the topologically trivial structure goes to the cold, all the others go to the hot direction. Moving to the cold direction is what is more usual, say, in the soft matter business. So if you have somewhere Brownian motion at the temperature gradient, you get nucleation at the cold end. Okay, so normally particles tend to move to the cold end. It simply means they are more moving in the hot direction than in the cold. So that means they have a higher probability to go to the left. And once they are in the cold, they move less. So there's an argument that normally diffusion goes to the cold direction. But here it's otherwise. So all the topologically non-trivial structures will move to the hot direction with some angle. And to make a long story short, how that works is explained in this graph. So that can be understood by a momentum transfer. So the temperature gradient creates a Magnon current. So assume there are Magnons now going from the hot to the cold end. They're moving, then they are scattered. And because of this scattering of the Magnons at this skyrmion, we get a force. Okay, that points in some direction. And because the Thiele equation has this cross product term, the resulting velocity is perpendicular to the force. And that explains the strange angle. So it depends on the scattering potential of the skyrmion and the scattering direction. You get this effective motion that can indeed point against the Magnon current. And that's it. With that, I'm already at the end. So that is the slide to say thank you to my group and to the many people we collaborate with on different aspects. So regarding skyrmions, most important is our collaboration with Matthias Klaui. His group in Mainz did these experiments on the diffusion, and there are many more papers on the anisotropy and other aspects from his group. And then there is also the collaboration with Laszlo Sündek. They are doing in Budapest these ab initio calculations where we get all these parameters, Jarzynska Maria and so on, interactions for our spin models from. And the other subjects we collaborate with many others. Of course, I also acknowledge the funding we get from different sources. And the last slide is a summary, maybe a short summary. So I talked about our work on skyrmions at finite temperature. So that was mostly it. We have this working horse, let's say, in our group, this strange system, a monolayer with a lot of DMI and frustrated exchange, where you can stabilize different topological charges. So we can really investigate how a topological charge, 1, 2, -1 or so, affects the dynamics of the system. And then I talk mostly about this Brownian motion. One can use it in a reshuffler device. It's a collaboration with Matthias Klaui. I showed that the diffusion becomes anisotropic. Some other, I can talk about it, but some other effects are also anisotropic then, like in the skyrmion Hall angle and so on. I explained the Thiele equation, how you can use it or not, or you can extend it to take into account the Magnonic contribution. And the last work was on temperature gradients and the topological dependence convenants. And with that, I'm at the end, and I thank you everybody for listening here. So thank you and for the invitation as well.
All right, thank you so much. So on behalf of everyone, I'd like to clap for your excellent talk, really summarizing the current developments, and in particularly this the Nernst angle from skyrmions. I think this is very exciting and probably a very new idea. And okay, we will have more discussions. Before we go to the question answer, may I request Uli to stop sharing, and I request all of you to switch on your camera. We take a screenshot, and then we will have the question answer. Thank you. Wolfgang, I think his camera is not working. Yeah, now we see Wolfgang. Great. Please look at the camera. Yes. Your camera is to the right. Yeah, that's better. Okay, I take picture now. It's good to see. All right. Cool. Okay. Okay, I think we got it. Thank you so much all. You may kindly turn off your camera and I request Uli to again share your screen. So please write or raise hand if you have a question. So let me begin with from the end part of the talk, where you talked about the skyrmion-Nernst angle. So is it experimentally already observed or it's a theoretical idea?
There's some work going on experimentally, and I'm not sure experimentally. Theoretically, yes. Some of it is cited here. So the point is the theoretical results scatter a bit. I mean, some of them could only investigate one skyrmionic topological charge, let's say one or so. Some of the theory made different assumptions, not momentum transfer, but angular momentum transfer, then you get different results. So that's an interesting point here. So I think the results are quite different in different theories. At least we can say that we have the theory, the analytical one, resting on the Thiele equation plus simulation. So at least that agrees. But regarding experiments, no, there's not much. The point is, in experiments, much of the dynamics is defect dominated. So mostly, for example, diffusive motion to investigate is very difficult. There's not much work done. They do this in Mainz, and some other groups are also trying, but you need a very good film with a low defect density. Otherwise, the skyrmions are normally pinned as defects.
I see. Well, I see no more.
With the current, you can push them so strong that they move. And with the temperature gradient, it seems to be more tricky.
Okay. I have a very simple question. So you are talking about the trivial structure Q equal to 0. As we know, the skyrmion, it also has a Q equal to 0. Or some people call it the target skyrmions. So skyrmion inside another skyrmion, it has a Q equal to 0. So do you expect similar like Nernst angle and all that with respect to a skyrmion?
Yeah, we did some to start with some early simulations of skyrmions as well. And it looked, but that's not published, but it looked always like they have Q equals 0 and follow the Thiele equation. Yeah.
Yeah.
So it seems really to be so.
Okay.
They follow the theory of Thiele with Q equals 0. So in that sense, yeah, that's right. In the temperature range, they would really move in a different direction. That would be funny to see. Yeah.
Yeah, I mean, this is very nice. Well, I don't want to take all the questions. So if there are questions, please raise hand or write in case you want me to read it. In the meantime, I can just ask some questions which I find very tricky. So now this Brownian motion, what you see, I'm aware of that paper, and Matthias has also presented in his talk experimental point of view. So I wonder if you take any other type of skyrmions, like skyrmion or with different Q. Do you expect that Brownian motion to happen?
Yes, I would, and I would say the same as before. Namely, the skyrmion with the topological charge 0 would probably follow this curve, which is funny. That would be a nice effect because you see they are so different. Q equals 0. That should be fine, yeah. if you manage to measure that. As I said, the problem is always the defects. So they in experiment they do not follow exactly this theory, this simple theory, because the defects act as energy things. So you have energy barriers that have to be overcome, and your diffusion coefficient will not just be linear in temperature; it will be like exponential with energy barriers. So it's a bit more complicated, but we would expect to see this difference in the topological charge. Yeah.
Yeah, and logically thinking, if your skyrmion size is bigger, then the Brownian motion will be like less, isn't it?
If they are bigger, then that means in this formula, let's say in that one, that means that D is larger.
Yeah. And
if the D is larger, yeah, it depends a bit on the ratio to G. I think in very large skyrmions, this D is much larger than D, but I'm not sure that alpha D is much larger. So it's tricky.
Okay.
But it could be that in the very large limit, it should go down the diffusion coefficient with size. Yeah. But I think the bigger effect is that the larger ones, they will catch more defects, let's say. That's probably the bigger effect.
That's also a more practical aspect, yeah? Yeah. So they will be more under the pinning potential, so to say. Mm-hmm, yeah. Mm-hmm. Okay, I see there is a question in the chat box. I will read it for you. Any particular significance of higher order topological charge fermions from Nilofer?
Even higher than that. So in that model, we can stabilize up to 3, at least in the simulations. No, I'm also not aware of other work on higher topological charges. But you see, for example, in that graph here, it doesn't make then much of a difference for the diffusion, I would say. So,
okay. So I think the answer to the question is probably they don't have any particular importance. So if they occur, they can still behave with the same dynamics, isn't it?
Yeah.
Yeah.
Yeah, and simulations, I'm not sure, but that might also apply to experiments. Also, the question is how stable can they be? I mean, they could fall apart in 3 single skyrmions, right?
Okay.
What you see, okay, did I have a picture of a Q equal to, I think I had one somewhere. Or was it here? Yeah, that's Q equal 2 at least. So I don't have Q equal 3 here. But you see, it could fall apart into skyrmions. And probably that can happen in simulations as well. So if you just simulate and calculate the topological charge, we would not see if that are 3 skyrmions or one texture that is close together with the charge 3. Okay. It's hard to distinguish, and the experiment is probably even worse.
Okay. Well, I have a very simple question from an experimentalist point of view. You are using the atomistic simulation because they are very appropriate, not only to do the smaller structure, but also, most importantly, for antiferromagnetic skyrmions, where the exchange length is very less. I wonder, from micromagnetic point of view, now is it like possible to consider the small exchange length for antiferromagnetic skyrmions, or one has to use the atomistic simulations?
Yeah, the main advantage of the atomistic simulations is that you have a realistic lattice structure, and that means your Magnon spectrum is, let's say, correct. You get the right dispersion relation. Yeah. In micromagnetic simulations, if you do that with a stochastic force, you don't have the real dispersion relation. You only get the long wavelength limit. And with that, you don't get, let's say, a real phase transitions and critical behavior at that. But you would see, of course, diffusive motion as well, micromagnetically. So we use it as well. We do that when we want to make the connection to experiments, because, for example, the skyrmions in Matthias Chloe's group, they are rather big. We cannot simulate that atomistically. We can say that in general, we would see this effect or so. But if we really want to calculate, let's say, for our equations, this D or this G,
Yeah.
Then we do that micromagnetically for the experimental system, and then you can plug it in the formula.
Okay.
So it makes some sense to do that as well. Yeah.
But still, the antiferromagnetic skyrmions you cannot do with micromagnetic, isn't it?
If you really want an antiferromagnetic lattice structure, not. If you want a synthetic antiferromagnet,
That's possible.
Yeah, that would be better probably. We do that as well, by the way. We work on it. I didn't show it. We're trying to publish currently also with experiments, but we work on antiferromagnetic experiments as well. Yeah.
Okay.
So roughly they are also in the Q equal to 0 class for the 3D equation.
Okay. All right. So I don't see more questions. If you have any questions, kindly raise hand. We can take 1 or 2 more questions. I think the talk was very clear. So, or if you have any questions, I'm sure you can write an email to Uli, and I'm sure after his holidays, probably you will be able to answer that. And I think it's time. Thank you. So I will share my screen to present a small memento to you.
Okay.
Yes. Well, it was very nice to have you in 2018 December in the IC Magma conference. I hope you again can come to our institute someday.
Yeah, I would like to.
This is a digital memento. I will read it for you on behalf of our WTS team. So WTS seminar webinar series on spintronics, National Institute of Science, Education and Research, NISER, Bhubaneswar, India. Takes pleasure in presenting this plaque to Professor Ulrich Nowak from University of Constance from Germany, in recognition and appreciation for being a valuable speaker to give a lecture on stochastic dynamics of topological spin textures. So thank you so much, Uli. I will send you the soft copy of it. And on behalf of everyone, I'd like to thank you again for taking the trouble to give this talk from your holiday. I wish you a wonderful vacation. And hopefully once you come back, you can join again the seminars. And I thank all the participants today for joining the seminar and making this a success. So see you next week. Next week, I think we have Olaf Helbig is giving, Professor Olaf Helbig. So another colleague from Germany, who is an experimentalist working on synthetic antiferromagnets and stuff like that. And yeah, so then see you around. Please stay healthy and happy, and see you next week. Thank you, Ulrich. Thank you, Ulrich, so much.
Thank you, and goodbye.
Bye-bye. Have a nice evening. Bye-bye.
Yeah, you too.
Good night, day, all of you. Bye-bye. Cheers.